All right, welcome back. This is Stephen Creech, and today we will be continuing on our discussion of hyperfields. We are doing section 2 today, so this is preliminaries. And so kind of the outline, we'll talk about hyperfields, quotient hyperfields, what it means to have a strong or weak extension of hyperfields, and then talk a little bit about polynomials over hyperfields and roots to hyperfields. I guess hyperfields, a bit of history, they were developed by Krasner in 1956, and their generalization of fields kind of, I hinted that the addition is now multi-valued. So here we're going to give our first definition of what a hyperfield is. So a hyperfield is the following data. So we can think of it as sort of a 5-tuple consisting of the following. The underlying set K, some addition operation, some multiplication operation, a 0 and a 1, where 0 and 1 are kind of, well, they're elements of K that should satisfy what 0 and 1 satisfy. And it satisfies the following conditions. So the first condition is we define K star to be K set minus 0. So all the non-zero elements of our field. So if I consider our non-zero elements under multiplication and with 1, this is an abelian group. So all this is saying is when I consider my non-zero elements under multiplication, it's commutative, and it satisfies all your group axioms that you want multiplication to satisfy, and 1 is the identity element. So multiplication remains unchanged. The other thing about multiplication, if I take some elements of my hyperfield K, we have 0 times x is x times 0, which is just 0. So in some sense, 0 is an absorbing element. And maybe I should say what these things are. So kind of 0 and 1 just live in K, but plus is a binary operator, but it goes into the power set. Well, I put an X here to say a non-empty subsets of K. And this O times is just a normal binary operator. So all of this should make sense. So multiplication, it behaves how we like. And it plays with addition, whatever addition means, in the usual way. We have our distributive laws. So if I have an XYZ in K, we require if I take X times Y plus Z, well, this really should just be X times Y plus X times Z. And similarly, if I have X plus Y times Z, this really should be X times Z plus Y times Z. And in some sense, you have to make sense of what this left-hand side means, because this is an element, and this will end up being a set. And it's just the naive thing where you say, oh, an element times a set is just take every element of this set and multiply it on the left by this element x. So we have our distribution laws like normal. And then lastly, we require k with our addition operator and 0. This forms an commutative hypergroup. So just like with rings and fields, how addition is an abelian group under addition with 0 as the identity, similar thing in the hyperfields case, except we now have to be a hypergroup. But I have not told you what a hypergroup is. So a hypergroup has the following axioms, which should be thought of as similar to the group axioms, but just an extension. So we need that plus is associative. That is x plus y plus z is equal to x plus y plus z. And again, we have to, this here is a set. This is an element. So I have to make sense of what does it mean for a set to be added to an element. And all this means is if A is a subset of K, then A plus little x is just the union of all elements of here, A and x, of A plus x. And similarly, you can extend this to saying if A and B are subsets of K, then A plus B is just the union over, well, A and B of A plus B, because these are all sets. And so this allows you to kind of recursively build up what we mean when we're adding lots of things together. And you can just do this in a way that's a bit more detailed in the paper, but I will just leave it at that here. So B, so we have, so we're commutative, this is associative, it will also be commutative if we're a commutative hypergroup. So that just means, you know, x plus y is y plus x, as you would expect. 0 is an additive identity. So what we mean by this is, well, 0 plus x should be x plus 0. Well, this really should be x. However, since this has to be a function to a set, it's really the set containing x, which shouldn't be a surprise. And if you kind of think about what this means with sort of this associativity, adding 0 won't do anything. So, good. We now need inverses. And the way we define inverses is as follows. So for every element in our hyperfield, there's a unique element that we denote by negative x in K, such that 0 is an element of the set x plus negative x. So because we have the sum of two elements is a set, the additive inverse, we don't require it to be equal to 0. We don't have two things add together to equal 0. We just need that it's an element of the set. And this should look like all the group axioms. However, there is an additional axiom called the reversibility axiom, which says if I have some element x, and it's in the sum x plus z, this is true if and only if, so if we think of this as an equation like x is equal to y plus z, well, I could subtract y from both sides, and I could also subtract x from both sides. So this is true if and only if the element negative y is in the set negative x plus z. And this kind of assures, so this is called reversibility. And in some sense, if you can use this reversibility to convince yourself that if 0 is in the sum x plus y, then really y is negative x. So, good. So I've told you what a hyperfield is. So it's just going to be a field, or a set with an addition and multiplication. But multiplication behaves the usual way, but the real interesting part is sort of the addition is now allowed to be multi-valued. So let me begin by giving you some examples. So, example. Probably the first example and silliest example, since these are generalizations of fields, a field is a hyperfield. So if F is a field, it is also a hyperfield, where we just define our sum x plus y in sort of the hyperfield sense to be the sum x plus y, where this is it in the field sense. And then multiplication is just going to be your usual multiplication of fields, or that's given in this field structure, and then you can go and check that with this definition, it satisfies all these axioms. So the second example, which might be the first interesting example, that's is what's called the Krasner hyperfield. So we denote the Krasner hyperfield with a boldface K, and it is the following. As a set, it contains two elements, 0 and 1. And we can think about, well, how must things act if we want? So I could probably make some multiplication tables. So if I have to multiply two things, well, 0 times anything has to be 0, 1 times 1 has to be 1, so our multiplication's forced here. As for addition, we have our 0, we have our 1, we have our 0, we have our 1. Sort of by this axiom of addition, we're forced 0 plus 0 is going to be 0. Really, it's the set containing 0, but I'm going to just omit the curly braces. So I must have this. And 1 plus 1, well, 1 has to have some additive inverse, so I need a 0 here. However, if I just keep it like this, this is the integers mod 2, so I will say 1 plus 1 is both 0 and 1. And this is the first example of a non-trivial hyperfield. So we now can see what makes a hyperfield different. 1 plus 1, it is simultaneously 0 and 1. It is the set 0 and 1. And so this is the first non-trivial example of a hyperfield. Let me give you another example. So this is called the hyperfield of sines. And I denote this with a black bold S. And here, this has three elements, 0, 1, and negative 1. And the way I like to explain the hyperfield of signs is, well, it has this word sign here. So this should make you think of a sign of a number. So is it positive, is it negative, or is it 0? So if we start building our multiplication tables, 2, 0, 1, minus 1, 0, 1, minus 1, well, in some sense we're forced 0 times anything has to be 0. 1 has to be an additive, or a multiplicative identity. Negative 1 has to have an inverse. So in some sense, this is the only multiplication table that can be allowed here, which hopefully is fine. And what we can do is here's how I like to think about this. If you take 0 and you multiply it by anything, it's 0. So 1 times 1 is 1. If you take two positive numbers and you multiply them together, it's still positive. If you take a positive and a negative and you multiply them together, it's negative, right? If you take a negative and a negative, it's positive. So that's kind of what's going on here. As for addition, we know what we have to fill in for our 0 and 1. Our 0 plus anything just has to be itself. So now the interesting part is 1 plus 1. So 1 plus 1, in some sense, it is what happens when you take a positive number and you add it to a positive number. It stays positive, so 1 plus 1 will be 1. Similarly, negative 1 plus negative 1, if I take a negative number and I add a negative number, it remains negative. The interesting part is if I take a positive number and I add it to a negative number, well, it could either be positive, it could be negative, or it could be 0. So for example, 1 plus negative 1 is 0. 1 plus negative 2 is negative 1, right? Negative 1 plus 2 is 1. So it could either be positive, negative, or 0. So in this case, the 1 plus negative 1, it's all three at the same time. And that's kind of how we think of the hyperfield of signs. So that's our next example. Here is another example, our last example before I tell you about quotient hyperfields, and this is called the weak hyperfield of signs. And I denote this with a blackboard W here. And what is the weak hyperfield of signs? It is exactly the same as the hyperfield of signs. So I will just copy our tables for the hyperfield of signs. However, we make one small difference in that 1 plus 1 is now 1 and negative 1, and similarly, negative 1 plus negative 1 is also 1 and negative 1. And so that is the weak hyperfield of signs. And I will explain why this, in some sense, we call it the weak hyperfield of signs when we talk about extensions. Because in some sense, this is a weak extension of the hyperfield of signs. So hopefully this gives you a sense of what hyperfields are and how addition acts on hyperfields. All right, so moving on. I will now tell you what a quotient hyperfield is. So this next section is on quotient hyperfields. And the idea is we can construct a hyperfield from a field. So this was actually Krasner originally came up with this construction, and he actually had conjectured that all such hyperfields can be constructed in such a way. So every hyperfield is a quotient hyperfield. However, it was Masner, I believe, who proved that there exist non-quotient hyperfields. And I believe Matt Baker, he actually had this conjecture that the majority of all hyperfields are non-quotient hyperfields. So if you kind of look at the density of like the size of the number of quotient hyperfields of a given order to all hyperfields of a given order, that goes to 0 in the limits. That is still an open question, though. So let's go over this construction. So kind of what we do, so we start with a field, F. So we take a field F, and then we take G, a subgroup of the multiplicative group of F. And we define an equivalence relation. So the equivalence relation is X is related to Y if and only if we have some elements of our group G such that, well, X is G times Y. So X and Y are the same up to multiplication by some element of our group. And what we will do is we'll let sort of X in brackets be the equivalence class. Of little x under our equivalence. So these are sort of just the cosets of F star mod G, because these are groups, and so this is a group, that's a subgroup, so it makes sense. However, we have to have another equivalence class, the equivalence class of 0, because really this equivalence relation right here is only on F star, so we'll just put 0 in its own equivalence class. So we have our equivalence relation. We know what it is everywhere. And we construct, so the quotient hyperfield, we will denote it F modded out by G. So has as elements the cosets above. So yes, we have our elements, and now I just have to tell you how multiplication and addition are defined. So first is if I take the coset x and I multiply that by the coset y, this is just going to be the coset of x times y. And in some sense, all this is saying here is our multiplication, well, if you put 0 in, this is just going to be 0. if you take non-zero elements, it's just the multiplication inherited by doing f star mod g. So we now know how to multiply things. It's just inherited. The more interesting one is addition, as things tend to be with hyperfields. So the equivalence class of z will be inside the equivalence class of x plus the equivalence class of y, if and only if I can find some element in the equivalence class of z where, well, some element in the equivalence class of x and some element in the equivalence class of y, such that z prime is x prime plus y prime. So all this is saying is this equivalence class is in this sum if there's a representative here who's a sum of two representatives of each of those equivalence classes. So this is how Krasner defined a quotient hyperfield, and then he actually went ahead and showed this satisfies all the hyperfield axioms, so I will not do that here. There is one comment I have on how this, how I like to think about this addition. So if we think of x and y as sets, then what we can do is consider the set sum, so to say, of x and y. So this is the set of elements x prime plus y prime, where x prime is in the equivalence class of x, and y prime is in the equivalence class of y. So this is a set. Then it's equivalent to say that x plus y will just be the set of equivalence classes z, such that z is in sort of this set sum of x plus y. So I like to think of it, take your two cosets, add them together in all possible ways, and then those representatives, it will be that the set of all those representatives will be the set. And so this is a quotient hyperfield. So I have this comment in the paper. When we're working with quotient hyperfields, we make the convention to denote the elements of K actually using this equivalence class notation. So we can distinguish between the coset and the actual element X, which lives in the field rather than the hyperfield. So these quotient hyperfields, they should not be new to us in any way. We can see some examples. So fields are quotient hyperfields. So if I let f, so if my field is f, then if G, it has to be a subgroup of the multiplicative group. So I will let G just be the multiplicative identity. Then what happens is f mod G is just going to be, well, I really shouldn't say isomorphic to f. It's, in some sense, our equivalence relation, x is equivalent to y, if and only if x is equal to y. And so the equivalence class of any element x is just going to be the set x. And then we can kind of see, well, through this definition here, the sums are just going to behave as, if I take the equivalence class of x plus the equivalence class of y, well, this is just the set Z such that Z is in the equivalence class of x plus y. But this is just equal to, well, what's the equivalence class of x plus y? It's just going to be, well, the equivalence class of x is just the set x. The equivalence class of y is just the set y. So x plus y should just be the set x plus y. So this is the same as saying this is the set x plus y. So this is exactly how we saw a field as a hyperfield, where the hyper summation is just the normal summation, but you just put curly brackets around it. So we have fields. The next one is our Krasner hyperfield. So in some sense, this is one extreme. We took our subgroup G to be as small as possible. So what if we take G to be as large as possible? If we think about what that means is x is equivalent, well, if I have two non-zero elements, they must be equivalent. So this is saying non-zero elements are equivalent. And then we can go ahead and say this gives us two representatives, 0 and 1, where 0 is just the set 0, 1 corresponds to all of, this 1 is really equal to everything else. And then we can see, I guess there's a caveat if F is the field of two elements, then I guess F star is just 1, and then we're back in the fields case. So assume F has at least 3 elements. If we take F star and add it to itself, its multiplicative inverse has to live in there somewhere. So we have to end up back where we started. Actually, you might need F doesn't have characteristic 2. That might be the condition you need. I haven't thought about that too much. But the point remains. This gives us back, for most fields F, not characteristic 2. This should give us back what we want. So the next one I want to say is the hyperfield of signs. So here, what we can do is we can view our hyperfield of signs as take the real numbers and mod out by the multiplicative subgroup of the positive real numbers. So what we do when we think about what this equivalence relation says is, well, given 1, the equivalence class of 1 will just be all the numbers which are greater than 0, because they have to differ by some positive element, so you get all the positive real numbers. We know 0 has to be 0, and then -1, well, it'll be -1 times all the positive real numbers, so this will give us all the negative real numbers. And in some sense, we can now understand this table here as in sort of the quotient sense. Because when I said, oh, a positive plus a negative, it's either 0, positive, or negative. Well, if I take the set of all positive real numbers and the set of all negative real numbers, if I take their set sum, I'm going to get the set of all real numbers, which contains positive, negatives, and zeros. So that's one way to view this. So the hyperfield of signs also a quotient hyperfield. Here, now the weak hyperfield of signs. This is actually an important example. So, we can say the weak hyperfield of signs has a quotient structure of take a field of p elements and mod out by the squares. But you have to pick p a prime, where p is greater than or equal to 7. And we need p to be equivalent to 3 mod 4. And in some sense, this right here is going to be the important thing for showing that we don't have a minimal extension in general. Because what we'll do is we will say, we'll take our weak hyperfield of signs, and we'll pick two different primes. We'll pick 7 and I think 11, and we'll cook up two different extensions and show these two extensions. They're not, the minimal extensions containing roots, they're not the same. And that will be enough to give us non-existence. So sort of the fact that this has multiple different quotient structures is the key into our second theorem. Is there a way to see this? So if p is a prime and p is 3 mod 4, this has something to do with whether -1 is a quadratic residue or not mod p. Give me 1 second. So -1 is not a quadratic residue. So what's happening here, so here we need this to say -1 on p is -1. So that's why we have the 3 mod 4 condition. I think the greater than 7 condition is so we don't run into things like our Krasner hyperfield where we're just modding out by either everything or just the identity. So what happens is our fp mod fp star, we're going to have 1, this is the set of quadratic residues. -1 will be the set of quadratic non-residues. And then 0 will end up being just the set containing 0. And we can check 0 has to add correctly. The only way you are going to get, if I add two sets together, the only way you can get 0, since -1's a quadratic non-residue, it makes sense that it's here. So we kind of have partitioned our residues and non-residues apart. So 1 plus -1, well, that has to have 0. And it should still get, there's probably some counting argument where you can get all residues and non-residues. And similarly, when you add these to itself, you should be able to do some sort of counting argument to say, oh, I will have some quadratic residue as well as some quadratic non-residue. Because there's only, like, what, p minus 1 over 2 residues / non-residues. And when you add these things, there has to be a certain number, which is probably greater than p minus 1 over 2 elements in those sets. So that's why we need this 3 mod 4. It's so the equivalence class of -1 is actually the quadratic non-residues. And -1, we need -1 to live in the set of quadratic non-residues. So these are the hyperfields that we saw. So previously, and sort of this weak hyperfield of signs will be the key for the second theorem, let me tell you another hyperfield, which will be sort of the key to the first theorem. And this hyperfield was kind of the inspiration. So if we go to the hyperfield of signs, it's like the real numbers modded out by the positive reals. So this example is called the phase hyperfield. And I denote this with P. I know P is probably more for projective space, but what it is here, this is going to be the complex numbers modded out by the positive reals. And so, in some sense, this was the inspiration for finding extensions for quotient hyperfields, because if I take the real numbers, I don't know how to extend it in the hyperfield case in general, but I can extend it in the field case. So if I extend the reals to the complex and mod out by the same subgroup. That's going to be the general construction later on, and we'll go into that later. So this was kind of the key inspiration example to finding these extensions. So the way I like to picture this is if we think of the complex numbers as sort of the complex plane, we have 0. So this is our 0. And then we also have our unit circle S1. And in some sense, it's called the phase hyperfield because the phase is the angle, and it's like for each angle, so if, maybe I can use a different color here. So for example, this angle here, its equivalence class is everything on this ray. So it's everything on this ray. So this is like the equivalence class of X. And so the way addition works is if I add anything with 0, it's 0. If I take kind of the antipodal angle, this will then be sort of my negative x. And so x plus negative x should just be x, negative x, and 0, because if I add any two things along this line, it has to stay along this line. But it could be on either side. So this tells me x plus negative x is the set 0, x, negative x. And this should be similar. 1 plus negative 1 is the set 1, 0, negative 1. And how addition works for angles is if I have, say, this here is y, then if you think about what x plus y is, it should just be all the angles in between. So this should be x plus y. It's all the angles in between. But then what would happen if I chose something, say, right here? So if I do this one, or maybe I'll keep this color. So if this here is z, so you just have to choose the smaller of the two arcs. So this would then be x plus z. And so this is the phase hyperfield. So that's it for what hyperfields are and what quotient hyperfields are. So now we're moving into the next section. So this is called strong and weak extensions. So the notion here is addition is multi-valued. So there are kind of two ways we can define a homomorphism. Kind of, we could require addition to be inclusion of sets, or we could require it to be equality of sets. So here, we will let K and L be hyperfields. And I will kind of use subscripts to denote where addition and multiplication lie. So we say a function phi from K to L is a weak hyperfield homomorphism if it satisfies the following. So we need phi of 0 is 0. So this is like the 0 in K, this is the 0 in L. Phi of 1 is 1. Again, this is like the 1 in K, this is the 1 in L. We need, so how we will have, if we add two things in K, well, this should just be the same thing as adding them in L after applying our homomorphism. But what makes it weak is the inclusion. Makes it weak. And then the last thing is multiplication has to obey how it does. And then we call phi a strong hyperfield homomorphism if, I guess, in addition, it's really 3 with what I had initially wrote with an equality. So this makes it strong. So here's one remark that is interesting. If you recall from classical field theory, every homomorphism must be injective. Kind of, you can show the kernel must always be trivial, and yeah, so it's like you really only care about extensions. That's not the case here. So homomorphisms need not be injective. So, for example, given if K is any hyperfield, you can show that you can map it to the Krasner hyperfield, where you just send 0 to 0, and anything else to 1, where x is not equal to 0. And really, I should say weak here. So these weak extensions don't need to be injective, which already makes hyperfields a bit more strange than fields. So we can now define extensions. So if I have K and L are hyperfields, we say L is a weak hyperfield extension of K if there is. So one thing we want to avoid is sort of this example here, because this would, if we just required there to be a homomorphism from K to L, that would let the Krasner hyperfield always be a weak extension. So we're going to require there to be an injective homomorphism. So kind of injectivity will be what is required. Phi from K to L. Oh, and I need the word weak here. And we will call K a weak subhyperfield of L. And similarly, L is a strong hyperfield extension if there is an injective strong homomorphism phi from K to L, and we'll call K a strong subhyperfield. And it's clear to see our notion of saying things are strong and weak makes sense, since every strong hyperfield extension is a weak hyperfield extension, due to the fact that a strong hyperfield homomorphism, well, equality implies inclusion. So strong hyperfield homomorphism will imply weak hyperfield homomorphism. So this terminology of strong and weak should make sense. So let's give a couple of examples of an extension. So the weak hyperfield of sines is a weak extension of the hyperfield of sines. And this is just given by the homomorphism, which sends 1 to 1, and 0 to 0, and -1 to -1. So if we come back up here, and we look at our table of elements, our addition and multiplication table, clearly multiplication is the same for both of them. So if we consider the map between the hyperfield of sines to the weak hyperfield of sines, well, we have it's strong everywhere, except at 1 and -1, because 1 plus 1, if you do that in the hyperfield of sines, you're just going to get 1. But that's a subset of 1 plus 1 in the weak hyperfield of sines, which is 1 and -1. So since we have that inclusion, the weak hyperfield of sines will be is a weak extension of the hyperfield of sines. So this kind of shows us an example. What we're more interested in is kind of the phase hyperfield, which was the C mod r greater than 0, is a strong extension of the hyperfield of signs, which we saw was this R modded out by the positives. And we can see that sort of by our picture of this. If we think about what happens if I have this -1 and 1 here, if you just consider this set 0, 1, and -1, however you add them together, just sitting inside the unit circle, you're just going to get your if you just consider these three elements of the phase hyperfield, that'll be exactly your hyperfield of signs. So we now have an example of our extensions. We have a weak extension, we have a strong extension. This weak extension will be the key to the no minimal extensions. The strong extension will be our key to finding strong extensions. And yeah, is there anything else to say here? I think that's, oh, yeah, so we're about to get to our first lemma, which kind of looks at our phase hyperfield and makes the observation. Look, we have our phase hyperfield. We consider it as the complex modded out by the positive reals. Hyperfield of signs is R modded out by the positive reals. They're both modded out by the same subgroup. So here is the lemma. For a field extension, so if L is an extension of the field F, and if I take G, a subgroup of the multiplicative group of F, then we'll have that L modded out by G is a strong extension of F modded out by G, where these have the natural quotient hyperfield structures. So this is going to be one of the main lemmas in the proof of the main theorem. So let's prove it. So we'll define our strong homomorphism. So we'll have our homomorphism from F mod G into L mod G as follows. Well, if I take the equivalence class of X in F mod G, I'll just take that to be the equivalence class of X in L mod G. So kind of the first thing to show is we will show that the equivalence class of X, when we think of this as an element of F mod G, is the same as the equivalence class of X when we think of this in terms of L mod G. I mean, this is a bit clear, since if we think about it, the equivalence class of X in F mod G, this is just going to be the set of X times G, where G is in G. And these are elements of F here. But this is exactly the same as the equivalence class of X in L mod G, except these are now allowed to be elements of L. But since X is in F and G is in G, which is the subset of X, all of these elements will still be the same. So we have that the equivalence class of X in F mod G is the same as the equivalence class of X in L mod G. So that will be enough to show us that we are injective in this extension. And we can also say this yeah, because the multiplicative subgroups are the same, this will be fine. And we are now going to drop the subscripts of L mod G and F mod G. And this gives us the functions well defined. So we just have to check multiplication and addition. So if I take phi and I apply this to f mod g times y, well, on the one hand, this is phi of x times y, because the multiplication in f mod g is just you multiply them. And we know that how our phi is defined, this is just going to be the equivalence class of xy. But the equivalence class of xy, this is going to be the equivalence class of x times the equivalence class of y. Thinking of this in L mod g, but this is just phi of x times phi of y. Yeah. And that is the proof that multiplication behaves the same. So as for addition, so this is a multiplication, it works. Basically, it's just inherited from, we're modding out by the same group. As for addition, if I consider x, and if I add that to f mod g to y, on the one hand, this is the set phi of the set of z, equivalence classes of z, such that z is in the set sum of x plus y. So this is going to be, as a set, the set of equivalence classes of z, such that z is in x plus y. But this is exactly equal to, if I take x and I add it to y in L mod g, because these two are elements of f. And this is exactly phi of x added to phi of y. So we have equality of the addition and multiplication, and we'll have that it's injective and well-defined and all those lovely things. And that gives us that we have our strong extension of hyperfields. And this lemma will be the key in proving our main results. So I've told you about quotient hyperfields, extensions, and kind of the last piece of the puzzle is polynomials over hyperfields. So here's the issue with polynomials and actually trying to define them. You'll run into a bit of issues if you think about how things multiply together. You know, in field theory or ring theory, you have a ring, you take polynomials over the ring, and that's another ring. But for hyperfields, it's not exactly going to work that way, because the issue is addition being multi-valued and multiplication being single-valued. When you start to take polynomials, if you multiply two polynomials together, you have cross terms. And those cross terms have additions involved. So multiplication now no longer becomes single-valued. It will now become a multi-valued operation. So this will be something completely different. So let's define this. So a polynomial over a hyperfield K And I use capital T for my variables for polynomials over hyperfields. I will be using X for my variables over fields. So all it is a formal sum of the form in variable t. I take a sum from, say, I equals 0 to n of ai t to the I, where I do the thing that you have for most polynomials. I require my ai's to be in my hyperfield K, and we denote the set of polynomials over K in variable t as K adjoin T. So similar to how you denote it for rings. So we'll prove, let's see, yeah. Here is the next issue that you come across is the following. So we know what it means to be a root of a polynomial. Something you plug in and you get 0. However, for hyperfields, you plug something in and you get a set. So for a polynomial over a hyperfield, we say C is a root of little k if 0 is in the set K of C. That is going to be, when I mean K of C, if I have some element of our hyperfield, I can plug that into the variable t just as you would for a normal polynomial. There's some evaluation of the polynomial over our hyperfield. And you can actually study what it means. So yeah. Baker had this paper with, who was the other author? Oliver Lorscheid, on sort of this notion of multiplicity of roots for these polynomials over hyperfields as well. So here's kind of the phenomenon I was referring to in an example. So if we consider the hyperfield of sines, let's consider the polynomial 1 plus t and the polynomial negative 1 plus t. So if I were to multiply these together, 1 plus t times negative 1 plus t, what happens? So if I multiply them kind of with all the cross terms, I'm going to get a negative 1 plus negative 1 times t, which I'll call negative t, plus positive 1 times t, so I get a t, plus a t squared. So one might call this negative 1 plus negative 1 plus 1 times t plus t squared. So in some sense, this should be thought of as the set negative 1 plus t squared, negative 1 plus t squared, negative 1 minus t plus t squared. So kind of this negative 1 plus 1 in the middle, kind of this cross term here is what's causing multiplication to no longer be single valued. So this is no longer a hyperfield or even a hyperring. But there are people who've studied sort of things that have both multi-valued addition and multiplication. So I'm now going to define. So let K be a quotient hyperfield f mod G. If I take a polynomial f in the variable x, we're going to define the induced polynomial. I will denote this f bar in K of t as follows. So if I have f of x, and it is the sum from I equals 0 to n of ai x to the I, this will give me the polynomial f bar of t, which is going to be the hypersummation of, well, I'm going to take the equivalence classes of those AIs and then t to the I. And kind of the goal, which we will talk about next time, is how can we, if I have a polynomial in a field, or no, in a hyperfield that has no roots, can I lift that back up to a field? And kind of using classical field theory in our construction. So this is all the preliminaries. We kind of talked about what a hyperfield is, what are quotient hyperfields, what are extensions in both the weak and strong sense, and kind of what these polynomials are and how, what a root is and how these things are weird. So yeah, that's it for this video. We'll actually prove the first theorem next time. Thanks for watching.